Welcome back. We are finishing up with the divide and conquer this week. In the second lecture, we will see the definition of the subset sum problem and set the stage of solving it by solving the pair sum problem first using divide and conquer. So yes, we are spending 2 lectures solving one problem, so it must be non-trivial. Let's dive in. The subset sum problem is among those problems that are generally considered to be extremely difficult to solve, and yes, it is NP complete. Its definition states like this. Given a set S of n integers and a target value k, does S have a subset that sums to k? Let's look at an example set S here. It has numbers 4, 3, 6, 1, 7, for instance, and then the target value k is, let's say, 10. So do we have a subset of S that sums up to 10? Yes. So we have 4 plus 6. We also have 3 plus 7. So subset sum is a decision problem, and it is also NP complete. If you are interested, you can see its proof in the textbook. Now you may wonder, why are we even talking about this problem here? We know a polynomial time algorithm to this problem doesn't exist. So we will show that even for NP-complete problems like subset sum, divide and conquer strategy can still help improve the efficiency. First, let's see the naive brute force algorithm for subset sum. We can enumerate all possible subsets of this set S. So how many subsets are there? For instance, if we have S with 1, 2, 3 elements, then its subset would be 1, 2, 3, 1, 2, 1, 3, 2, 3, or 1, 2, and 3. So when we look at each element in the set S, it's either in or not in a subset. So we have 2 possibilities for the first element. We also have 2 possibilities for the second element. It's either in a subset or not in a subset. And the same for the third one. So the number of subsets of set S is 2 to the power of n, where n is the size of the set S. We can enumerate all 2 to the power of n possible subsets and compute their sums during the enumeration process. So this naive brute force algorithm has a complexity of big O of 2 to the power of n. It's an exponential algorithm. With that baseline, now we ask, can we do better than exponential when we know we cannot get to polynomial? What about using our good old friend divide and conquer strategy? Before we attempt to design a divide and conquer algorithm for subset sum, we need to set the stage and solve a much simpler and related problem first. This problem is the pair sum problem. Given a set S of n integers and a target value k, does S contain a pair of elements that sum to k? Is pair sum solvable in polynomial time? Given a set S of n integers, we need to choose 2 numbers out of n. So we know we can have this enumeration done in n squared time. So the pair sum problem can be solved in polynomial time. Can we do better than this? A better algorithm for pair sum is to start by sorting all the integers in S. Then we work through the sorted list from both ends, eliminating values when we determine they cannot be in a pair that sums to k. So for instance, once we have sort S, we can write it as S1, S2, S3, Sn, where we have S1 less than or equal to S2, S3. We start by computing T equals S1 plus Sn. And there are three possibilities. When T equals K, we can stop since we have found a pair that sums to K. If T is less than K, we know S1 cannot be in a solution. It is too small. Even adding S1 with the largest number in the set, Sn, we still have a sum less than K. So we can just discard S1 and move on and check S2. On the other hand, if T is greater than K, we know Sn cannot be in the solution. It is too large. Adding it with the smallest number in the set, S1, is still greater than K, so we can discard Sn and move on and check Sn minus 1. Therefore, after one addition, we either stop with the solution or we eliminate either the smallest or the largest element of the set. We can continue in exactly the same way on the remaining n-1 elements. This pseudocode of the algorithm looks like this. We use two pointers L and R to help narrow down the search in each iteration. This while loop executes at most n times, and each iteration takes constant time to compute an addition and performs a comparison. This algorithm thus runs in big O of n log n plus big O of n time, because sorting requires n log n time, and the rest of the algorithm requires big O of n time. So overall complexity would be n log n. Now we have seen an efficient algorithm to solve the PairSum problem. Next, we see an extension of this problem. This is the two-set PairSum problem. Given two sets, x and y, of integers and a target value k, can we find a number x from set x and a number y from set y, such that x plus y equals k? Is there a polynomial time algorithm for the two-set PairSum problem? It should be clear that we can solve it using an algorithm very similar to the one we used to solve the PairSum problem. We start by sorting both sets, x and y, in an ascending order. We compute the sum of x1 and yn, where x1 is the smallest number in set x and yn is the largest number in set y. We compare T with the target K. If they are equal, we have found the pair and we can stop. If T is less than K, we know X1 is too small, since adding it with the largest number in Y is still less than K. So we need a larger number from X. We can discard X1 and move on and check the sum of X2 and Yn. On the other hand, if T is greater than K, we know Yn is too large, since adding it with the smallest value in X is still too large. We can remove Yn and move on and check the sum of X1 and Yn-1. The pseudocode of this smart two-set PairSum algorithm then looks like this. Now the input has two sets, x and y, and one target value k. We start with sorting numbers both in x and y in ascending order. This will take us big O of n log n time. Here we have two pointers again, L and R. Note that we control the while loop based on the size of set x. We could also use the size of set y instead. It does not really matter. We stop the loop when one set is exhausted. So what's the complexity of this algorithm? It will be the same as the previous one. We have big O of n for the while loop, and we have big O of n log n for the sorting. So the overall complexity of this algorithm would be big O of n times log n again. That'll be all for this lecture. Please try and implement these really interesting algorithms and try some of the exercise questions from the textbook as well. Next step, we will finally get to the NP-complete problem subset sum, and we'll see how divide and conquer works its wonder. Stay tuned.